All right, now we're going to talk about tropical weather systems. And tropical are kind of different, shall we say, than what you normally see in the mid-latitudes. They do get up here, tropical weather systems, and impact our weather significantly when they do. But let's just understand a little bit about what's different about them. So what conditions are actually required for tropical cyclones to form? Well, first, consider the tropics. 23.5 degrees north, 23.5 degrees south, basically where the sun gets vertical. There are no fronts that pass down in there, so the air mass is uniformly warm, humid. High temperatures, diurnal temperature variations typically is greater than the monthly mean variation. So that means over the course of the year, what they see in one day, that temperature variation, they don't see over the course of the whole year. So what happens is thunderstorms align in small tropical clusters sometimes, easterly waves, and they literally look like mid-latitude squall lines. Many, many times the intertropical convergence zones were this. Oh yeah, one interesting thing is the analysis that's done down there. Most meteorologists do not use isobars. Why? Because the pressure is uniform. There's not a lot of pressure change across the tropics. So what do? We look at what we call streamlines. A streamline is just taking the winds and drawing a line with the wind flow. So you look at those winds barbs and just start a line at one station, try to follow it to the next station, and you'll basically make a curved line and maybe several lines that might come to an area that shows convergence or divergence. But this is a way to find things like small easterly waves which occur in the tropics. Hurricanes are the intense cyclones. They usually occur late summer to early fall, and one thing for a hurricane to have, it must be greater than or equal to 74 mile per hour winds. So let's contrast them with an extratropical cyclone. We've dealt with those in the mid-latitudes. Extratropical cyclones have a strong temperature gradient. Look what? Hurricanes are uniformly warm and humid air mass. No fronts. The central pressure in a hurricane many times is lower than that in an extratropical cyclone, and the pressure gradient near the center is almost always significantly greater. That's why the winds are so much stronger. They're also a much smaller system, where an extratropical cyclone might cover 1,000 miles. A hurricane may only cover a couple hundred miles. Oh yeah, and they're warm core, which means the circulation weakens with altitude. Unlike the extratropical cyclone, they got colder and more intense with height. These get warm and they get less intense. And a matter of fact, at the top of most hurricanes is an anticyclone. So here you can see the eye and the eye wall literally around it from an aircraft. Diameters can range anywhere. I've seen them as small as 2. This says to 46. And guess what? It really doesn't matter how small that eye is all the time as to how intense this hurricane is. Sometimes the smaller eyes are the more intense. Sometimes a little bit bigger eye can still have the same intensity. So here is a picture of a hurricane. It has spiral bands that rotate into it. What you're seeing out here in these spiral bands is convergence and little bands of showers or thunderstorms developing in these bands. And they gradually rotate closer and closer, and they get closer together as you get into the core of the storm. When you have a hurricane approach you, you may have a band of showers out here, maybe a couple hundred miles out ahead of the storm, the main eye. Then you may get another one, maybe 50 miles further in. And then all of a sudden they get closer together and more intense, and the rain gets stronger. And the winds start picking up, and eventually you get under the main part of the storm, and you have periods of very heavy rain and lots of wind. One of the necessary conditions is you need relatively high sea surface temperatures. Guess what? Sea surface temperatures are abnormally warm again this year. That's why many places are forecasting already that we'll have another significant hurricane, tropical storm cyclone season. One other thing you need is Coriolis effect and weak winds aloft. That Coriolis effect kind of limits where tropical cyclones can form down to the equator. You would think, oh, they would form down around the equator and stuff, since that might be the hottest place. But they don't. They actually got to form at least 5 degrees north because they need Coriolis effect, or 5 degrees south. You need weak winds aloft. You don't want these thunderstorms getting sheared apart like happens in the mid-latitudes where you have strong winds and you have vertical wind shear. Here you want weak winds all the way, and it's got to be very humid air mass. And one of the things is SST's got to be greater than 80 degrees through at least 150 feet depth. That's saying you got to have a lot of warm water. And here you can actually see some of the places currents picked up on satellite here off the east coast of the U.S., the Gulf Stream, where you have the warm water there. Some eddy currents and loop currents around the Caribbean that can really get temperatures into the 90s and really strong depth of warm water. Guess which area gets it first? The first area that's going to get warm is the Gulf of Mexico and the southern part of the Gulf Stream. They're going to be the first areas because they're close to land, get a lot of sunshine, and they're shallower. So they're going to be areas that heat up first. And that weak winds aloft doesn't let them get it torn apart. El Nino encourages much stronger winds aloft. So when you have an El Nino year, you tend to have less hurricanes. This year we have a La Nina year, so we have the opposite impact. So on average, there are more hurricanes in the western Pacific Ocean than there are in the Atlantic and Caribbean. Typically, more hurricanes form out there each year and less over the Atlantic or the Atlantic Ocean. And as part of that, the Atlantic has hurricanes moving towards the west. So what do? They tend to impact the U.S. While as those over the Pacific Ocean that form off of Mexico, for example, are going to tend to move westward out into the middle of the Pacific. So they don't tend to impact the U.S. However, the Hawaiian Islands can sometimes get ice picked up on one, but it's a rare event. And you can see here where they kind of tend to move away from here, whereas over our area, the east coast of the U.S., more of them. This is our frequency in the United States. Notice late August to mid-September is really the peak season. We get some earlier in the year. You don't. And they're going to tend to form in the Caribbean or right along the South Florida coast. But as later in the year, temperatures get warmer, they really start picking up in August and settle off in October, and then they really peak. So you can actually see the breeding grounds. You start off near the U.S. As the ocean begins to warm, you get more and more waves coming off of Africa that begin to form longer-lived hurricanes. And eventually, you get the longest ones in September to October, and then they move back towards the coast and gradually dissipate. Tropical disturbances or easterly waves. One of the interesting things about them is you see this low pressure. It drives to the north here. This is actually a trough of low pressure. And most of the precipitation occurs on the east side of the easterly wave, not on the west side out ahead. So sometimes Saharan air layer will make a mess of a hurricane. Saharan layer comes off of Sahara, and what it is a dry, dusty, stable air originating over the Sahara Desert. It has a lot of hot temperatures aloft, and now it's moved over really what is a cooler ocean, so it becomes even more stable at the low levels. It's dry, so it helps the stability as well. So both of these things tend to inhibit cyclones or even destroy a hurricane when it comes in contact with it. What you really want is a lot of water vapor getting condensed into the storm. Get the cooling going as it's rising. Air triggers more condensation, releases more latent heat. And divergence aloft, allowing the air to really rise. Here is your categories. Tropical depression, anything with sustained winds greater than 23 miles per hour. Oh yeah, and it's got to be a circulation. It can't just be sustained winds. It's got to be a low pressure that you can identify. Tropical storm, where we begin to get a name, is 39, and hurricanes are 74. And here you can see all the different hazards and the damages caused by them. Storm surge is the main death. Rain, think about it, they form over a tropical ocean. They're going to have a lot of moisture with them. precipitable water many times are well over 2 inches in these, which is extremely high. They dump tremendous amounts of rain when they come inland, especially if they get into the mountains, like the mountains of Western Virginia. When Agnes came into it, for example, in one 24-hour period had 35 inches of rainfall in some of the mountains, caused the worst flooding ever in Virginia with a lot of deaths. And here you can see, for example, how the flooding hit Port Arthur, Texas. And you can see the massive amount of rainfall. Even though this storm was a hurricane when it came inland, it weakened graphically, but it kept pulling moisture in. Remember the counterclockwise circulation right off the Gulf of Mexico into the Houston area and caused tremendous rainfall. There are pressure vortices or whirlwinds sometimes in the center and causing more damage, but the pressure gradient force is very, very high in a hurricane. So winds diminish when they hit land. Think about it, friction. It'll lower the wind speed at the surface. However, the winds aloft might continue stronger. What that does is allow for wind shear to develop. And you remember, you're having thunderstorms in a hurricane. Even out in the outer bands, you have cumulus clouds rising into the atmosphere. So you've created an environment, particularly in the right front quadrant of the storm motion, where tornadoes can actually develop. Some hurricanes have a significant number, others do not. Storm surge is another big problem. It's a wind-driven, literally dome of water. Think about it this way. If you have sea level, and guess what? You got a question on this today in your discussion this week. Here's your sea level. When the wind keeps coming from the east, what happens? Water keeps piling up here. So that sea level, instead of being here, rises we'll say 6 meters, 18 feet, which is not out of the realm of possibilities. So instead of sea level being here, it's now up here. Oh yeah, this house is now below sea level. And guess what? There's waves on top of that. You had to have 100, 150 mile an hour winds. They're going to produce waves. One of the things, though, is say that hurricane came into your north. This sea level, winds are pushing offshore. You might actually get a lower sea level because your winds have been pushing the water out. So there's no trouble for the house. So just a few miles difference can make a major difference in how big this sea level rise is. And if you came in at time of high tide might be a whole 1 meter higher. Well, you just added a meter onto the 6. So now you're 7 meters up on storm surge maybe. And guess what? Hurricane Sandy that you're going to tell me all about in a couple of weeks had that happen. It came in at high tide. It had a tremendous amount of wind field that came in from the southeast, pushing into New York City. So you had a significant storm surge with it because of that huge wind field, and it hit at a time of high tide. And you can actually see the devastation here. Look at it before, look at after, and how the water literally got all the way back to that road and in there. So if anybody had been living in this area, you can see the destruction that occurred. This was Michael. Camille brought a tremendous storm surge. Sandy, the largest Atlantic hurricane on record in size, 12.7-foot storm surge at Kings Point, New York. These stronger winds, now we've got some what we call the slosh model. And it has actually been upgraded for this next hurricane season. And we get probabilistic storm surges out of it in exact areas that we expect to be covered by so much water. So there are challenges. Oh yeah, the historical record, well, we averaged so many hurricanes from 1995 to 2019. Guess what? That average went up from 1970 to 1994. Well, it's going to go up again because we've had more. And there is a new set of normals coming out this year in May. And here we can see how the Atlantic multi-decadal oscillation makes a difference. When you have the cold water, like we had in the 60s and 70s, you didn't have many hurricanes. And now we've got warmer water. We have a lot more hurricanes. ENSO plays a role. And one of the things about climate change is when they've been trying to model looking at it in the future, what they found was that, oh, there may not be that actually an increase in the number of storms, but think about it. The air is warmer, holds more water, so there is an increase in rainfall rates, and the intensity actually went up. There's a higher probability of category 4 and 5 storms in the future than there are now. One of the things about that occurred in the past, when we had that law in the 1970s and 80s, a lot of people built up along the east coast of the southeast coast of the U.S., and that continued, that population rise. So to evacuate people now can be a real issue. Barrier islands definitely play a role in keeping things at bay. Think about the Outer Banks. They actually act like a barrier island for a lot of the mainland along North Carolina coast, so that the storm surge is going to hit that barrier island, it's going to destroy it, but actually be weaker by the time it gets into the mainland. There's actually a barrier island here in Virginia Beach area as well. Sandbridge is one. There's another one that actually was formed by a hurricane, Willoughby Split. Interestingly, it could go away in a hurricane sometime. And there's about 500 houses to 1,000 houses built on that right now. Evacuation can take all forms. You can get gridlock. For example, in Virginia Beach area, we're more familiar with, in Hampton Roads, there are about 2.5 million people that live here. If we have to evacuate for a Category 4 hurricane, they estimate it will take, transforming all roads to westbound, 72 hours to evacuate everybody that needs to be evacuated. Not a good possibility. So, one of the things that long-range forecasting, Colorado State's already issued theirs. The Hurricane Center will issue one. Another thing, we talk about accumulated storm index. What that really is measuring how many Category 4s and 5s or 3s. How many of those did you get and how many days were they there? It gives you an idea of the total energy of hurricanes. So that maybe you get a whole bunch of Category 1 hurricanes one year, but the next year you may get several Category 4s and 5s. You may actually have the same energy both years. Project Storm Surrey was a waste. It occurred back in the 60s and early 80s. What they tried to do was siege hurricane clouds, thinking that that would cause the eye wall to expand. Well, first, clouds are warm. These are warm systems, so there's not a lot of silver iodide crystals that are going to cause icing. So that didn't work real well. And second, they discovered that eye walls actually go through a transformation. They can go contract in, and they can reform outwards and then come back in again. So that none of this whole project worked. So with that, the only last thing I wanted to quickly show you, this was last year's map of all the hurricanes that took place. You can see all of them going across here in this part of the world, and all of them up and down through. Really, the Gulf Coast got clobbered last year. And this is just an image of one of the last storms, Hurricane Ada. Look at the bands. One band way out here, another one here, another one here. You can actually see them in the infrared, and another several to the east. And they go around like this, feeding into this core region. This is a very intense, and here you can actually see the eye. So if you have any questions about this, please don't hesitate to ask.